Hello and welcome to example 6. We are still looking at page 115 in the workbook. And this is our second example of finding an integral using the substitution rule. Okay, it really takes seeing some examples to get comfortable with this process. So let's work through this together. Okay, so using the same method that we did for example 5, we're going to start this process by making a u substitution. And generally, choosing a u to be inside of another function is a good strategy. So we're going to let u equal 1 plus x squared because it just happens to live underneath this square root. Okay, making it a kind of a natural choice. Okay, and as in example 5, once you make your choice for u, the next step is always to take the derivative of that u. Okay, so the derivative of u is equal to, let's see, derivative of 1 plus x squared is 2x. And I'm going to go ahead and move the dx to the other side of the equation immediately. We broke that step into two parts in the last problem. So du over dx is 2x. We just moved the dx to the right-hand side. Okay, and then like we did in example 5, we will algebraically solve for the dx by just dividing through by the 2x. Okay, so we get du over 2x equals dx. Okay, and again, the two calculations that interest us are these, what u is equal to and what dx is equal to. So we'll go back to the integral that we started with and see if we can rewrite it by substituting. All right, we've got two substitutions that we need to make. One was that the 1 plus x squared we called u, and the other one was we noticed when we calculated that dx is du over 2x. Okay, so if we go ahead and just make those two substitutions, we're going to get the integral of x square root of u. We rewrote the 1 plus x squared, and the dx was equal to du over 2x. Okay, do you notice any cancellation here? Okay, well, we've got an x in the numerator and the denominator. Those go away. And so if we rewrite this, we've got the square root of u times du over 2. Notice that there are no x's left over in our integral. And when you're using this method, that's what we want. Okay, the sign of having made a successful substitution is that you get your integral in terms of the new variable u. There are no x's left over. Okay, and so what it comes down to is can we calculate this integral that's in front of us? Okay, well, one thing that might make it a little bit easier is to notice that this 2 down here is a constant. That's really a 1 over 2. And so we can pull constants outside of integrals. So I'm going to take that over 2 and pull it outside as a 1/2. And what's left is 1/2 times the integral of the square root of u du. Okay, I'm going to remind you of the fact that the square root of u can actually be written as a power, u to the 1/2. Okay, so let's rewrite that square root of u as u to the 1/2 before we go on. And notice that we've managed to take the integral that we started with up here and turn it into a much easier integral, just u to the 1/2. So can we find an antiderivative for the function u to the 1/2? Well, let's go back to our table of kind of common antiderivative formulas. Turn the page here. And do you see a formula on that list that you think might help us find an antiderivative for u to the 1/2? That really matches this first formula, the power rule. The n is just the power of 1/2 in this case. Okay, so we're going to use the power rule, which says basically to get an antiderivative, we need to raise the power by 1 and divide by the new power. Okay, so if we do that here, we're going to get 1/2. Our power in this case is 1/2, so if we raise that power by 1, we're going to get u to the 3/2 divided by 3/2, and this is an indefinite integral, so there's going to be a plus c at the end. Okay, so can we simplify that? First observation maybe is that if we divide by 3/2, that's the same as multiplying by 2/3. So I'm going to rewrite this like this. And the last step is we should really substitute back in, as we've got an answer that has u's in it. We'd like our answer to have x's in it. So remember what u is equal to. Way up here at the first step, it's 1 plus x squared. So we're going to substitute that back in to get our final answer. Okay, and finally, it might be natural to notice that these 2's cancel. So let's do that as well. And we can write our answer in a little bit nicer of a form like this. 1/3, 1 plus x squared to the 3/2 plus c. Okay, and that's our answer. Okay, now I want to make one comment though before we quit here. You might be asking yourself in these first couple of examples, where did the u come from? Okay, at the beginning of the problem, how do we know what to choose the u? Okay, well, there's no hard and fast rule that will always work, but I can give you a couple of guidelines that might help you. Okay, we need to page ahead a few pages here, so bear with me. Okay, so at the top of page 117, makes some kind of general comments about the substitution rule. Okay, this is meant to give us some advice as to how to choose a u. Okay, so for example, number 1, when making a substitution, well, this is just more of a general comment about kind of what the overall strategy, why the substitution rule works the way it does. So remember that the goal is to transform an existing integral into an easier integral. You saw that in both of the examples that we did. Number 2 is about how do we choose a good u? Okay, 2 general guidelines that I can give you is to choose your u so that the du, the derivative, appears somewhere in your integrand. If that happens, it's a good sign that you chose a good u. Okay, and B, another guideline is choose u to be the inside of a function. You might notice that that was the general strategy that we used in both of the examples that we did so far. Okay, so as we can continue to do examples, you're going to see those ideas motivating our choices for u.